And that's on surface integrals. So just as a reminder, if S is a surface parameterized by R of UV, with these vector components X of UV, Y of UV, and Z of UV. Okay. And I can give limits on U and V if I like. So I can say A less than or equal to U less than or equal to B, C less than or equal to V less than or equal to B. Oops. Like that. Then just to remind you, ds here is just RU cross RV, du dv. This is a vector differential for surface area. So it's a vector surface area differential. And that means that it's normal to the surface. Cross product is always perpendicular to both vectors, and those are tangent vectors. Okay. And then ds, the scalar, is the magnitude of RU cross RV. And that gets a du dv also. And so this is just the surface area differential. Okay, we need those both of those in surface integrals. And then don't forget, we also did if S is, oh, I didn't need to say if twice. Okay, so if S is parameterized more as a Z is a function of X and Y, and then we can have limits on X and Y. And these don't have to, this doesn't have to be a rectangular domain for X and Y. But just for the heck of it, I've done that. Then don't forget that we've come up with a couple of different things in this context. The ds, the vector, was, I think it was negative fx, negative fy, 1 dA. That was the upward normal. Okay. And ds could equivalently be fx, fy, and negative 1. Because the z component's negative, that's pointing downward. So that's the downward normal. Okay. And it just depends on the context of what you're doing. Sometimes you'll want an upward normal, sometimes you'll want a downward normal. Okay. And then we're thinking of these in terms of flux. And the normal tends to point in the same direction as fluid flow, or just whatever the direction of your field is, but not always. Okay, so you'll see this as we go. And then don't forget ds, the scalar, is the magnitude of ds. And this is a case, this is truth for every case. This is the magnitude of ds, the vector. And so we've said this is the square root of fx squared plus fy squared plus 1, and of course dA. Okay, so these are just sort of formulas that are good to have handy as you do surface integrals. So under surface integrals, there's a vector integral and a scalar integral. We'll do the scalar surface integral first. Okay, so you just do an integral. Actually, these are double integrals over a surface. And you're just integrating any old function, scalar valued, of 3 variables, and multiplying by surface area. That's it. Some function times the surface area. Okay. Now normally F could represent mass density. So this would be the mass of a surface, something that has very little thickness, basically. Okay, so this can be used to compute moments. I'll say any moments. It could be first moment, second moment. There are other moments as well. We'll just say moments. Moments of inertia, don't forget, and center of mass. For a shell, basically. A shell-like surface, how about that? Okay. If it has mass, then it has a center of mass, and it has moments, and it has a moment of inertia. If you're going to spin it, think of a hollow sphere. If you want to know the moment of inertia of a hollow sphere, like a globe that you spin on an axis, the moment of inertia would be a surface integral because it's just a shell. The sphere is hollow. So you have to do with this. It's a double integral, not a triple integral. Okay. Any questions? Let me see what I've got here for examples. I guess we should just lay out what this represents. So if S is R of UV as defined above, this is just all about substitutions. So you would do double integral over S of f of xyz ds. So you do a double integral. This would be f of x of uv, y of uv, z of uv, like that. And then you'd have to multiply by the magnitude of RU cross RV, like that. Let me get some space, and then I'm going to put a du dv outside of all that. Maybe I'll do dv du, somehow that sounds better to me. And then I put limits on v as being, I think we had, well, u went from a to b and v from c to d. So it's just a double integral, but all the points you're integrating over are on some surface. Okay, and you're just adding up the function everywhere on the surface and multiplying by surface area. Okay, again, you would do that if the function you were evaluating was density, and if it's density, if the density is mass per unit of surface area, and you multiply that by surface area, then you just get mass. Okay, so so you get that. Let's see if we've got an example here. Well, I'm going to set one up, and maybe not evaluate. Let's get it set up completely though. Okay, so little example here. Okay, so example, S equals a sphere of radius 3, centered at the origin. And I said sphere, I should have said spherical shell, forgive me. Please forgive me. Spherical shell of radius 3, centered at the origin, with mass density. At XYZ of, let's say, I think we do delta for density here, so delta of X, Y, Z, and I'll just do Z squared. Keep it simple. Okay. Now, the mass would be a double integral over the surface of the density. And this is density per unit area times area, but this is surface area, ds. Okay. Okay, any questions? So this is actually a lot more work than it looks. Easy enough to put the delta is z squared. So we have this double integral over the surface of just z squared ds. That looks so nice. Okay, but what the heck is ds on a sphere? Well, the funny thing is, it's sort of obvious. But I'm not going to do the obvious thing. We're just going to go ahead and bite the bullet and go the whole way. It's going to be horrible. So let's do the sphere. So we've talked about, this is sphere of radius 3. You know what, you guys, also I'm going to do another change. Let's just do a sphere of radius A so we can have this generalized. So up here, I've changed the radius to A. Okay. And so that this will work for any sphere for you. You can just substitute whatever, you know, if they want to do a radius 3 at some point, you can just change A to 3. Okay, so the sphere would be like an R of theta. I think I did phi theta before. And what we said was that the x coordinate is A sine phi cos theta. Y coordinate is A sine phi sine theta. And the z coordinate is A cos phi. Okay, like that. And we remember that phi ranges from 0 to pi, and theta from 0 to 2 pi. Oops. Okay, so that's sort of old news there. But I don't know what ds is. It's a surface area differential. I want to do ds to the vector first, and then we'll take its magnitude. Okay, so ds, the vector, not needed here, but it's ru cross rv du dv. Okay, and maybe while we're at it, we'll say ds, the scalar, is the magnitude of ds, the vector. Okay, so that's the magnitude of ru cross rv. Okay. Du dv. And it's 8:11. Okay, here we go. Let's do ru cross rv. First of all, ru. Our independent variables are phi and theta. So let's change these to phi and theta. Like that. Okay, and now we're going to do our phi. We've done something like this before, you may remember, in the context of Jacobians. It's been a while. Anyway, here goes our phi. So I'm going to do a cos phi cos theta, a cos phi sine theta. And then again, with respect to phi, you'll have a negative a sine phi. Okay. Okay. And now r theta. Forget it. Here we go. So r theta is going to have a negative a sine phi sine theta. A sine phi cos theta. And then the derivative of the z coordinate with respect to theta will be 0. Like that. Okay. We got to do this cross product. Not loving the idea, but here we go. R, and not the magnitude yet. We'll just do the cross product. R phi cross r theta. Okay, so here goes. Well, I feel like just sort of putting these in. So here are the coordinates for r phi. Okay, and then r theta. I'll let you guys catch up to that. All right, so these are the I's, J's, and K's. That. Any questions? Yeah, I mean, this totally reminds me of Jacobians. A little different. Okay, here we go. So for the I component, I'm going to do this way. So it looks like I'm just going to have an a squared sine squared phi cos theta. I'm going to double check that. Nothing, a square sine square phi cos theta. Yeah, so that's I. Now, the J looks like it may be similarly nice, minus J. Okay, so then I get a 0 and minus a double minus a negative. No, minus a double negative, so it would be a minus. A square sine square phi sine theta. Like that. I think the K part is, or the K part is the part that needs a little more work. Okay, so watch out now. Here comes the K component. We're multiplying diagonally here. So we're going to have an A square. There's going to be a sine phi, cos phi, cos square theta. Okay. And now the compression begins. See if I can pull this off. Not that much. Not bad. Kind of like that. Almost there. So the next component is I'm doing the upward multiplication, so that's going to be minus a negative, so this will become a positive. And you're going to have a square sine phi cos phi sine square theta. Look at that. Okay, so I don't know if you can tell, but there's a sine square plus cosine square and all of that. Let's do this in a couple of steps here. So the first component's got this a square sine square phi cos theta. The j component's got the a square sine square phi sine theta. Okay. The k component gets an a square sine phi cos phi. And then a cosine square plus sine square of theta. Like that. Now, I want to write this as, I want to factor out an A and a sine phi, I think. Okay, and what you get is a sine phi cos theta. And then there's an a sine phi sine theta. And then if you factor out a square, no, if you factor out a sine phi, you're going to have an a cos phi left inside. and the rest of the z coordinate is just 1. Okay. Now, if you look back, that's this. This thing right here is that thing. So, that's a position vector on the sphere. I might just back this up and say this right here is our r of phi comma theta. So this is a r sine phi. Is what that is. So ds, the vector ds, is r phi cross r theta, the phi d theta. Okay. But we just did the math, and that's a r sine phi d phi d theta. Oops, yeah. And r, that's the position vector. R of phi comma theta. Now that's handy to remember because we don't forget that ds, the scalar, is just the magnitude of ds, the vector. Okay. So this is just going to be the magnitude of a r sine phi. And I don't really want the d phi, and these are positive, so I don't need them inside. Okay, like that. Okay. And a is the radius, it's positive. Phi, you may remember phi is between 0 and pi, so sine phi, that's quadrant 1 and quadrant 2. So sine phi is greater than or equal to 0, with phi between 0 and pi. Okay. A is positive also. So the point is that I can rewrite ds as a magnitude of r times sine phi times d phi d theta. And what's the magnitude of r on a sphere? Anybody want to take a stab at that? Now remember, this is a surface integral. You live on the surface. You're not inside the sphere, you're on the sphere. And what's the radius of the sphere? Well, that would be the magnitude of r. So what's the magnitude of r? Anybody? Not getting anything? Again, the magnitude of r is the distance from the origin to a point on the sphere. That is by definition the radius of the sphere. So the magnitude of r is a, and therefore ds is a square sine phi d phi d theta. Remember, the radius of the sphere, the equation of the sphere is rho equals a on the sphere. So you're living on the sphere. Remember, you want to contrast this to dv is rho square sine phi d rho d phi d theta. So when you're inside of a sphere, or it doesn't even matter, when you're in spherical coordinates, d squared has a Jacobian that's rho square sine phi. But if you're on the surface of the sphere, then ds, because it's a shell, not a volume, ds is a square sine phi because rho is a on the sphere. Okay, so you're not allowing motion into the sphere, but phi and theta can vary, and ds is a square sine phi. Okay, any questions about that? Okay. So I have to go all the way back and evaluate my surface integral. So way back. Here it is. So I'm going to just copy this guy down. Okay. And come down here and just start evaluating stuff here. Okay, so double integral. Don't forget, on the sphere, z is a cos phi on the sphere. So when you do this double integral, z squared just becomes a cos phi. That's z squared. Okay. And then ds gets an a square sine phi. And now we can say d phi and d theta like that. Okay. And then phi, of course, from 0 to pi, and theta from 0 to 2 pi. Any questions about that? I don't know. We can try and evaluate this real quick. It doesn't look too bad. So it looks like we're going to have an a to the fourth coming out. And here comes the integral. This is all in phi. So I could do one integral from 0 to 2 pi just on d theta, like that. And then there's another integral here from 0 to pi of just cos square phi times sine phi d phi, like that. And then, of course, u will be cos phi. Okay, and so du will be negative sine phi d phi. Like that. And we can expect our limits to flip when we do that, but let's keep going. We got an a to the fourth, okay, times the integral of d theta from 0 to 2 pi, that'll just be 2 pi, okay, times the integral, I'm going to have a minus sign, I'll put it inside right now. So I'm going to have a cosine squared, which is u squared, and then a negative du, I guess. Remember, whenever the differential comes out negative, you can count on your limits being flipped around wrong. So this is negative, and so we see that when phi is 0, the cosine of phi is u. So cosine of 0 is 1. And when phi is pi, cosine is negative 1, right? So because those limits are backward, we have a negative differential that corrects that. Okay, so it kind of help you understand what differentials do. It keeps track of these transformations This is a transformation that's inverting our region, so the integral comes out negative.
Okay, so this is 2 pi a to the 4th. I guess we can put a 1/3 u to the 3rd from -1 to 1. I just kind of change the limits and make this whole thing positive. So it's 2 pi a to the 4th times 1/3, and you'll have a 1 to the 1 minus -1 here. So I guess we can finish this and say it's 2. Well, how about 4 pi a to the 4th over 3. Just like that. So that would be the mass of this hollow shell. So that's just sort of an example of a surface integral where you're adding up just on a surface. So that's kind of interesting. Let's do another example here where we go into the flux integrals. Okay, so just real quickly, we've already introduced scalar surface integrals. That looked like this. Double integral over a surface of some scalar valued function, like a mass density. Like I said, it could be a probability density function if you're trying to find the probability of a particle being on a surface, times surface area. Okay. So, and as we said, ds is that's the surface area differential. But then there's a vector surface integral. And this is the surface integral of a vector field over a surface. So the vector field would be like F over the surface S. Okay, so the integral looks really similar to double integral over the surface, but here we put a vector field in which has vector output. So big F of x, y, z, and then we're dotting that with ds, the surface differential vector. Okay, and then just maybe a quick kind of a reminder here. Probably there's a lot worth talking about on this. So let's go ahead and draw a little surface. And we'll put our, this is our surface S, okay? And just a real quick statement of what ds is again. Ds is just a unit normal. The unit normal gives direction to this surface area. Okay, so unit normal. And then this is the surface area differential. Okay. So if we want to plop one of those on here, it's going to kind of go like that. So that would be ds. Actually, I'm going to move over to the side here. And while I'm thinking about it, let's just do the unit normal here. Okay. And then we'll have ds be the area. So you may remember that ds is the magnitude of a cross product. So we're going to have like an RU du going in one direction. So I'll have this one be RU du, and the other one being RV dv. Okay, and then maybe we'll just make our little parallelogram that represents ds. Like that. And then ds is the area of this. That's too small. Like that. Okay, and then there's a field that's flowing across the surface. So we think of this as it could be like a magnetic field or an electric field. So let's go ahead and do our field, and let me make it a little thicker. So here's a field vector that's touching this surface at a point like that. Okay, and so the field is when you dot it with this unit normal, you're getting the normal component of the field. So let me go ahead and see if I can do a projection here. So I'm gonna tweak this picture a couple of times as I go through it. But I want to do the normal component of my field. So I'm trying to get a good perpendicular there. So just your patience as I pound this out. Okay, so that, actually I'm going to do one more cut on this. That's good. Okay, so when we do f dot in, we're just measuring how long the normal component is. So let me see if I can add some more here to make that clear. Okay, so from here to here. Oops. Okay, so what all I mean to say is that this distance right here, that's f dot n. Okay, so, and maybe just to put it down in words here, we've done projections many times, so I don't want to go over projections again, but f dot n is the component of f that's normal to s. Okay, so that's just the meaning of that part. Okay. And when you do f dot n ds, now you're multiplying by surface area. So f dot n ds, capital S there, is the normal component of f times the differential surface area. Oops, sorry about that. Let's see here, surface area. Okay, and this is called the flux differential. Okay, so if F is a velocity field of some fluid, so let's put this down. If F, and it doesn't usually, by the way, but this sort of gives us a feeling of what we're computing when we put it in the context of a fluid flow. So it's rarely a fluid; it's usually a field. But regardless, if F represents the velocity field of a fluid, let's say flowing through a porous surface. Let's say the porous, is that how you spell it? Surface. It could be like a filter. Oops. S, then flux is a total fluid, and I'll show you this later. It's a total fluid flowing across S per unit time. I should say flowing through S. That's probably a better word. Flowing through the filter, okay, per unit time. Okay, so you've got this flux differential, F dot NDS, so total flux of F through S, you would just sum up on this flux differential. So you do a double integral across the surface of F dot the unit normal ds, like that. But the unit normal times ds is just the ds vector differential. So like this, F dot ds this way. Okay. And so just as a reminder, the F field has to, is really a function of x, y, and z, which has component functions p, q, and r. Okay, so that is the field. So Harry, and then just a reminder that ds is Ru cross Rv du dv, or dv du in either order, where S is parametrized by R of uv. Okay. Not horrible. And this is not, what's the hardest thing here? It's not a new skill. These are just definitions. You know how to do double integrals. So the question is, if I ask you to compute the flux of a field through a surface, can you set the integral up? It's not, can you evaluate the integral? It is a little, but, setting this up, this is a challenge. Okay. Okay, so we're going to do a quick example. Okay, so here we go. Let's say our field has components x, y. Sorry, my bad. It's y, z, zx, xy, like that. The surface S has z equals x sine y. Okay, where x goes 0 to 2. And y goes from 0 to pi. Okay. So there was another scenario that I'm going to copy and paste down from our prior discussion. So let's see here. We also have this expression here that I'm going to copy back to our notes down below, because ds can take a different form depending on how it's defined. So let's just put this down below as part of our notes. You can just refer back up to it. in your notes. Okay, so I'm just going to put this in and kind of make it small. Oops. Okay, so this is our prior ds when z is a function of x and y. Okay, and of course you could have x as a function of y and z, etc. And you'd have to kind of alter the discussion here. Now I need to know whether this normal is upward or downward. I'm looking at my notes and it says we want to do an upward normal on this surface. Okay, which means we need to pick the ds from our prior discussion that has the upward normal. So here we go, ds is going to have negative fx, negative fy, 1 dA, like that. So the x sine y is our f of xy. Here. So we can go ahead and just start evaluating this. Negative fx, well, with respect to x, would be negative sine y. Okay. And then negative fy, that would be negative x cos y. And then the 1 that has a positive, it always got this positive z component. And we'll put our dA in here. Okay. Any questions? Now we're computing flux. Remember, flux is a double integral of f dot ds. Let's go ahead and do f dot ds real quick. We've got everything here. So the f again from above. We'll put down here, and then ds. We'll put there. That's a dot product. Could be ugly. Okay, so here goes. We're going to have a negative yz sine y. And then a negative x squared z cos y. And then just plus xy. That's horrible. And then dA. Only thing that's a little disturbing in all of this is that there's a z in here. So you can't have a double integral. Remember, the dA is going to be dy dx. Okay? And you can't have a z in there. So this is where you're going to have to remind yourself that z is x sine y. And do that substitution. So all of these integrals are all about just loads of substitutions. As you can see, we're doing one now. So I'm going to do a negative y, and z is an x sine y. So this is a negative x y sine y times another sine y. So it's going to be a sine square y. Now we've got an x squared z. So that's going to be an x to the third sine y cos y. Okay, and then plus the xy. And now dA. So I'm going to double check this to make sure it's not wrong. Okay. And so then the flux, I just got this from the book. So the flux, the total flux would be the double integral of f dot ds. Okay. It's easy enough to put limits on this. X goes from, well, first of all, I got this over the surface, so now we'll put this into a double integral with this big mess in here. Okay, and I don't think it really matters what order you do this in. I did y first, and then x. So y goes from 0 to pi, I think. And x from 0 to 2. So that's how you set up one of those monstrosities. I am just going to give you the answer to that one. I'm looking at all my work on this. This comes out as pi squared over 2. And we've evaluated a lot of double integrals. This one's already set up. The point is setting it up. Okay. Any questions? Let me know. And I'll be happy to talk to you during my office hours or something like that. Okay, I'd like to do Gauss's law real quick. Which is for flux of an inverse square. I'm putting this in a sort of a general context. Okay, so this is for flux of an inverse square field. Across a closed surface. S, and we'll go ahead and S containing the origin. Oops. We'll assume S is a sphere to simplify this, and then later on we'll talk about how it doesn't matter what the surface is. Okay, so we'll assume that S is a sphere of any radius. Let's say it's A. Okay? So, there's a convention, and that would be whenever we work with closed surfaces, the surface normal should point outward. So that's the ds vector, which is little n times ds. So you can think of that as the unit normal pointing outward, or ds, the vector pointing outward. They'll point in the same direction, and that needs to point out of the surface and not into the surface. Okay, so let's say should point outward. Now, if you point it inward, what happens is your dot product will come out with the opposite sign. It'll be negative when it should be positive, or vice versa. So it's not a big deal. You just change the sign of the answer, and nobody's going to make a huge fuss about this. But it's a convention, and you should try and remember it. Okay, so we've talked about inverse square fields. And that would be like in 16.1, I think we did the first one. So they look like this. Big F of x, y, z. The simplest version we said was some multiple of the position vector over the magnitude of the position vector to the third power. Okay. And how that came about, I think I'll leave you to go back and look it up. But you've got this k. The r, again, position vector is just x, y, z, like that. And the magnitude of that is the square root of x squared plus y squared plus z squared, but then you have to raise that to the third power. So you're going to do an x squared plus y squared plus z squared. Again, the square root of that to the third makes it a 3/2 exponent. Okay. And then the flux is going to be surprisingly easy to do because of some of the prior work that we've done to set up the surface of differential for a sphere. So here goes the flux. So doing a double integral over surface S, and when we put a circle around this, this implies S is a closed surface. That's standard math notation. Okay. And the surface integral for flux is f dot ds, like that. Okay, so we can go ahead and just put in our field. So actually, I'm going to put limits on this right away, I think. So I'll just do a double integral here. Now the field, I think I'd like to use the original form. This is k times r, the position vector, over the magnitude of the position vector to the third power, like that. Now ds, the vector differential for surface area, let's go back and find it because we already did this for a sphere. I think this is it here. So we want the vector differential, so that'll be this one right here that I'm wiggling about. Okay, so let me copy that, and we'll paste it down below. Okay, so you get an r dot r in there, so this is kind of an interesting outcome. We can go ahead and say, look, we're integrating over the surface of a sphere. Remember, there's no rho does not vary freely, so there's no d rho in this. You're stuck on the surface of the sphere. The only thing that really can vary is sort of your latitude and your longitude as you move on the sphere. But no, you're not going into the sphere, just over it. So you see phi and theta varying. Now, phi, of course, will have to go from 0 to pi, and for theta, you need to go from 0 to 2 pi as you move around the sphere. That's just the standard range for phi and theta as you move along a sphere in spherical coordinates. So let's do a little work on this here. So I see that r dot r. I kind of want to bring the a out and maybe the k. So let's do a, k, and then inside we've got this r dot r, and down below you've got a magnitude of r to the third, and then sine phi we're not going to get rid of. That has to stay, and then a d phi and a d theta. Okay. Put the limits in. Like that. Note r dot r, maybe over to the side, you may remember r dot r, I hope you remember, is the magnitude of r squared. Okay, so that's looking better. So we've got the magnitude of r squared over the magnitude of r to the third, and then the sine phi, d phi d theta. Okay, and of course we just get a 1 over the magnitude of r on that. It's interesting. Now, this is a sphere. So, motion is constrained to the surface of the sphere, which means that r does not vary randomly. Okay, so let's put this note in here. Motion is constrained. It is a surface integral. To the surface. So that means the magnitude of r has to be the radius of the sphere, which is a. Can you handle that? So that means I could get rid of that magnitude of r there. Now it's not your position vector that's constant. It's the magnitude of it that's constant. So you got this a k integral 0 to 2 pi, integral 0 to pi. This is just 1 over a sine phi d phi d theta. So the a cancels. Okay. Now, I like to think of clever things, if I can. Okay, so let's go ahead and write this down. This is a k, can't get around it. Integral of 0 to 2 pi. Integral of 0 to pi, and I just get sine phi d theta. Okay, that's fine. And you could do that. You could do the painful process. But I like to avoid integrating when I can, and I want to remind you just here, we're going to do a little trick here. So recall oops, that ds, and again, a lot of you guys, I wouldn't expect you all to recognize what I'm about to do. I've just been doing this so long that I know some of the tricks. So I know that ds, I think, if you go back to the notes, actually, let's just see it here. Okay, so did I ever say? Oh, here we go. ds, the scalar, is a square sine phi d theta. Okay, so I'm just looking at this thing right here. That's for a sphere, only for a sphere. That's the differential for surface area. Now that's the scalar differential, not the vector differential. A square sine phi. So let's try this. So ds, is a square sine phi d theta. Okay? And so what I want to do is I want to make this look like a ds. So what I'm going to do is I'm going to do a k over a squared, like that. And then this is integral 0 to 2 pi, integral 0 to pi. And then you're going to have an a square sine phi d theta. Okay, so this is just ds. It just looks so much like ds that I wanted to make it ds. Because in the end, you get this k over a squared, a double integral. You're still integrating over the sphere, just ds is what you're doing. Okay. You can even put this circle on here again. And this should just be the area of S. So you've got this k over a squared times the area of S. Okay. And so you have to know the area, the formula for the surface area of a sphere. Okay. So I would say, okay, that's pi times, what is it? 4 pi radius squared. Okay, so is k over a squared times 4 pi a squared. So that's the area of a sphere, surface area of a sphere. Okay, so in the end, you just get 4 pi k. Okay, and notice this is independent of the radius of the sphere. And so it's sort of interesting because, if you think about it, we think about flux as sort of fluid flow across some surface or through a surface. And so we've got this, some source of fluid on the inside of the sphere, spherical shell, that's flowing out across the shell. And all we're really saying here is it doesn't really matter how big the shell is, and in the end it doesn't really matter what shape the shell is. If you think about the flux, which is the total fluid flow, it's all going to flow across this sphere. It doesn't matter how big the sphere is, you're still going to have the same amount of fluid flowing through it. So this is basically a statement of Gauss's, what's called Gauss's law, that flux for the inverse squared field across this surface is going to be independent of the surface itself, as long as it's a closed surface and as long as it contains the origin, which is the source of the fluid flow. Okay? So that's Gauss's law. And it turns out to be independent of the surface altogether. as long as it's closed. There's just a lot of things in this class that sort of remind me of each other. Like we talked about in a conservative field. Well, inverse square fields are conservative. We talked about how in a conservative field that if you compute work from one point to another point that the field does to move something along a curve, it turns out it's independent of the curve. The only thing that matters is the change in potential energy at the endpoints. So when you do when you do work through a field that's conservative, it's independent of path, we say. And here we're saying that the flux is independent of the surface, and you'll see more of that